In this video, I'm going to cover how to code an approximator of definite integrals, or how to approximate the area under a curve. And before we do this, and I'm going to be using Python to actually write the code, before we do that, I want to first kind of just look at the concepts and algorithm we're going to use to actually create this code and write this code. So first, let's just look at some kind of arbitrary function, a function whose area we might approximate using our approximator. So let's start with this curve, y equals f of x. And we want to get the area from A to B. The way we're going to approximate this area, and by this area, I mean this thing, all this stuff right here. The way we're going to approximate that is by drawing a bunch of rectangles, like so, calculating the area of those rectangles, and then adding up the areas of all those rectangles, and we should get a value that's pretty close to the actual area under our function. So to start, before we start drawing our rectangles, let's first determine how many rectangles we want to use to approximate our area. Of course, the more rectangles we choose, the better our approximation will be. But for drawing purposes, I'm just going to do 3 rectangles. And to start with doing that, we first create 3 subintervals. We create the number of subintervals that is equal to the number of rectangles we will be using to approximate. So now that we have our 3 subintervals, we look at the first point in each subinterval, and then we evaluate our function, f, at that point, and that gives us the height of our rectangle in that subinterval. So for our first subinterval here, what we do is take f of A, and that will give us this point on the graph. And then we will make our base, the base of our rectangle, be the length of this subinterval here. So that will be the base of our rectangle. And now we have our first rectangle. Our second rectangle will be the same kind of deal. We're going to look at our second subinterval here, and we're going to look at the first point in this subinterval, and then we're going to evaluate our function f at that point, which will again give us this number here. We make that the height of our rectangle, and then we make our base the length of our subinterval, resulting in that rectangle there. And then we do the exact same thing for our third rectangle. Evaluate our function at the first point in the interval, and then make our base just the length of that subinterval. And now we have our 3 rectangles. And if we take the area of these 3 rectangles, we can see that it's pretty darn close to the area under the curve. It's not exact, of course, it is an approximation. So we have some overshoot here, an undershot here, and some more overshoot here. But all in all, it's not all that bad. So, of course, if we wanted to improve this approximation, we would just, instead of doing 3, we'd do 1,000,000 rectangles, and then we'd be basically equal to the area under the curve. So, okay, now we know kind of visually how we can approximate the area, but how do we actually calculate the area of these rectangles? Well, we need to know the base and the height of each of these rectangles. Let's first look at the base. Now, let's just say, for sake of argument, I drew all these intervals of equal length, and let's call that equal length delta x. So we have 3 subintervals, all of the length delta x, which consequently means that the base of all these rectangles here will be delta x. And because we have 3 subintervals, 3 rectangles, delta x here equals the length of our subinterval, b minus a, divided by our total rectangles, 3. And that expression gives us the value of delta x. Because, let's think about this, we want to fit 3 rectangles on the domain A to B. So, to make sure we can fit 3 rectangles in the length from A to B, we take our total length from A to B, which will be B minus A, and then we divide it by the total number of rectangles, in this case 3, and we get our delta x. So okay, now we have the base of our rectangles, now we need our height, and as was said earlier, the height of each of these rectangles is the first point in the subinterval evaluated, or our function evaluated at the first point in each of these subintervals. So for our first rectangle, we look at the first subinterval and then evaluate f at the first point in that subinterval, so f of a. So then the area of this first rectangle here is f of a, that's our height, multiplied by our base of delta x. And then to continue on approximating the area from A to B, we now have to add on the area of this second rectangle, which is looking at the first subinterval and then the second subinterval and the first point of the second subinterval right here. This point is at A plus delta x, because we started at A and we've gone over delta x. So f of A plus delta x. And then we multiply that height by our base to get our area, delta x. And now we've added up our first 2 rectangles, and now for our third one, same kind of deal. We're adding on our height times our base. In this case, our height is A plus, and now this time we've gone over 2 delta x's, not 1. And then we multiply by our delta x. So that is how we would approximate the area with 3 rectangles. And in general, the ith rectangle, so say if we were approximating using 1,000,000 rectangles, the ith rectangle, where I is just any numbered rectangle, the ith rectangle will be given by the height, which will be f of a, our starting point, plus I minus 1 times delta x, all multiplied by delta x, or this is our height, this is our base. And the reason we have I minus 1 here, and not just I for the ith rectangle, is we're starting at A, we're starting at point A. We're taking the first point of each subinterval. So for the first rectangle, we're starting at A. For the second rectangle, we're starting at A plus 1 delta x. For the third, we're starting at A plus 2 delta x, so on and so forth. So that's where we get I minus 1. And now that we have the value of our area for our ith rectangle, to get the area under our curve for n number of rectangles, and I need to make some space here, so I'm sorry this is going away. To get the total area under our curve f from A to B, we would sum up starting at I equals 1, so our first rectangle, all the way up to n. We're going to sum up f of A plus, remember our ith rectangle is given by this expression here, I minus 1 delta x, all multiplied by delta x, so again our height and our base, and iterating through this will give us our total area. Or I should say our approximate area. It's not going to exactly equal area, it's going to be approximate. So now I believe we have all of the tools that we need in order to actually write our code. So let us hop over to my command prompt. I'm going to start up a Python environment and we are going to get coding. So first, let's define our function here to actually approximate integrals. I'll just call this integral for now. And let's see, what parameters might we need here? Well, first, obviously, we need to know what function we're going to be integrating over, what function under which we are going to calculate the area. Let's call that f. We also need to know our starting and ending points. Let's call that a and b. And then lastly, I'm going to let the user of this function define how many rectangles will be used to approximate the area. So that way the user of this function can themselves weigh whether he or she wants faster computation time or more accuracy. So for starters, let's define what delta x equals, because delta x stays constant for all rectangles. The base of all rectangles is delta x. So just to clean up our code here, let's define our delta x to equal what it should be, which is the length of our entire interval divided by our number of rectangles, n. So that's our delta x. Now we're going to create a for loop that will sum up the areas of all the rectangles, add them together, and then we're going to return that sum. So to do that, before our for loop, we have to set and initialize an accumulator variable. Let's call it sum, and we're going to initialize it to 0 because we haven't added any rectangles yet, so the area right now is 0. Now, let us create our for loop for I, where I will be the ith rectangle, or not, yes, the ith rectangle. So for I in range, we're going to start at 1, and we're going to go all the way up to n. But in Python, this range function here, the end of the domain put into the range is exclusive, not inclusive. So if I put n, I will range from the values 1 all the way up to n minus 1. What I want is I to be a part of this domain here, 1 to n, to use mathematical notation. So to get that, I'm just going to add one more to this n. So now I will take on all the values from 1 all the way up to n, including n. So now we have our for loop. Now let's start adding to our sum. So we're going to say our sum, to add to our sum, we're going to type in our expression for the ith rectangle. And if we remember from the notes, that equals our function defined, our function evaluated at our starting point, plus how far over we've gone. And how far over we've gone is the ith rectangle, so I minus 1, all multiplied by delta x. And then we multiply that, our height here by our base, which equals delta x for all rectangles. So now we have the area of our ith rectangle, and we're adding that to our total sum. So now what that for loop will do for us is it will sum up all the rectangles, the area of all those rectangles, and then store them all in our sum variable. So to finish up our function here, we simply have to return our sum. So doing that, we should have a good function, assuming I didn't make any silly syntactic errors. Let's try it out. So to call this, where we have to first pass in a function, and a nice way to do that would be to use a lambda function. And this lambda thing, it's really nothing special. All this is saying here is lambda x. So a function that, when taking in an x, will return 2x. 2 times x is what I should write. So again, all that this lambda expression is saying is this is creating and returning a function. So I guess to write this in mathematical notation, this would be f of x equals 2x. That's what this lambda expression here is saying. So that's passing in our function. Next, we need our starting point. Let's start off at 0, and let's go all the way over to, let's make it 2. Now, let's determine how many rectangles we're going to use to approximate. Let's start with a smaller number, maybe 10. And let's see how it works. Oh, oops, I misspelled integral. Integral. There we go. And, well, let's see if this is correct, because we got a number. It worked, but is this number at all correct? Well, we know that what this will create, f of x equals 2x, is it will create a triangle. So going over 2, the base of our triangle will be 2. The height of our triangle will be 4. 2 times 4 is 8. Divided by 2, That's 4. So we should be getting about 4. So 3.6 isn't too off from 4. But let's see if we make this much higher, like say 1,000. We can see we got much closer. And then if we make this 10,000, we get even closer. And then the more zeros we add, the better. And also part of this has to do with the faulties of floating point arithmetic, but that's a whole nother topic. Point is, we have an approximator for the area under a curve, and I think that is pretty cool. So that concludes this video. Thank you for watching. I hope you come away from this video having learned something valuable. Goodbye.